In this lecture, let's talk about the Doppler shift and time dilation that can occur because of gravitation. And we'll understand this using the equivalence principle that we were just introduced to. So the equivalence principle actually can allow us to calculate a Doppler shift, and recall that a Doppler shift is a change in frequency that light, or electromagnetic radiation in general, undergoes when traveling through a gravitational field. So let's again consider an accelerating reference frame with a light wave sent from the floor of that reference frame to the ceiling. All right, so let's imagine our reference frame here is in a rocket again. We're going to send light from the floor sent to the ceiling. The height that the light will travel is a distance h. And this is a rocket's frame, so it's going to be accelerating. And the change in velocity of the rocket, by the time that, because it takes a finite amount of time for the light to go from the floor to the ceiling, the rocket will have accelerated in that time. And so its change in velocity will be just acceleration. Let's say it's constant acceleration a times t, the time it took for the light to go from the bottom to the top. That's how much the velocity will have changed. That's delta v. But you can think of it, therefore, that that's the velocity of the ceiling when the light gets there relative to the velocity of the floor when the light was first launched. The light was launched upward. The rocket frame was accelerating, so it's increasing its velocity. And by the time the light reaches the top, the ceiling's moving a bit faster by a times t. So the light is detected by a detector at the ceiling that is moving at some velocity v relative to the floor, effectively. Now, for accelerations much less, acceleration times time much less than the speed of light, then we can approximate the time it takes for light to get to the top of the rocket's reference frame is just h over c, the height over the velocity, which is the speed of light. And then there'll be smaller terms due to the finite time it took. And what I've been trying to say is effectively by the time the light reaches the ceiling is effectively receding, moving away with a velocity relative to the floor, with a velocity which is a times t, but time is just the height of the rocket, the distance light travels over the speed of light, so it's a h over c. So that's the effective velocity, or the velocity difference of the ceiling relative to the floor. But you can think of it as the velocity of the rocket when the light was first emitted, and then the velocity of the rocket when it was detected, and there was a difference in velocity there. The velocity increased. And that was a h over c, where a is the constant acceleration of the rocket, h over c is the time it takes to go from the floor to the ceiling. All right, let's fold this into what we know about the Doppler shift. Now, in relativity, we could derive the Doppler shift for electromagnetic waves, and in particular for a detector which is receding from a source. So the emitter and the source, sorry, the emitter and the detector have a relative velocity between them which is moving away from each other. Then the correct formula is this one, that the frequency that you detect the radiation is the frequency it was emitted at, f naught, times the square root of 1 minus v over c over 1 plus v over c. That was the formula. It gives you a frequency f which is less than f naught, and that's the correct case. The frequency is lowering if there's a receding velocity. And lowering frequency means, at least in the visible light, you're moving toward the red end of the spectrum, not the blue end. So we call this redshifted. So that was the formula that we've were able to derive in relativity, special relativity. I can rewrite this a little bit. I'm always allowed to multiply by 1. So inside the square root, let me multiply by 1 minus v over c over 1 minus v over c. That's obviously, that ratio is 1. But if I do it that way, in the numerator I have 1 minus v over c squared, which if I take the square root means, hey, I can pull it outside the square root. And in the denominator I have 1 minus v over c times 1 plus v over c. That gives me 1 minus v squared over c squared, all under the radical. But that's just the definition of gamma. Gamma is 1 over the square root 1 minus v squared over c squared. So I can just rewrite it as gamma, the relativistic gamma factor, times 1 minus v over c times the emitter frequency f naught for the receive frequency. But if I let this velocity be much less than the speed of light, we know gamma goes to 1. So let's set it approximately equal to 1. And, well, I won't set v over c to 0, but we'll let that correction stand. And so the frequency we receive the light at will be 1 minus v over c times f naught, the frequency it was emitted. If I want to think of that as a change in frequency, delta f over f naught, I need to take f and subtract off the initial frequency f naught. But that's essentially getting rid of the 1 term here, because this f is f naught minus v over c times f naught when I expand out the binomial. So f minus f naught is just minus v over c f naught. So delta f over f naught, which is f minus f naught over f naught, is just minus v over c. Quite simple. Now, from the previous slide, we saw that the ceiling is receding, and we calculated the velocity, the relative velocity difference of the ceiling with respect to the floor when it was emitted. So we can work out the velocity that we should put here in this formula for the Doppler shift, right? That was just a, the acceleration, times h over c, right? A times time, where time was h over c, the distance over the velocity. So we can do that. Let's plug that in. So delta f over f naught is minus a h over c. And remember, that was over c again right here. So it's minus a h over c squared. Which, now, if I say this accelerating frame is equivalent to a frame which has gravitational acceleration, and I set a equal to the acceleration due to gravity on the Earth's surface, little g, then that's telling me that the change in frequency, delta f over f naught, that relative change in frequency, is minus little g times h over c squared. What that means is, in a non-accelerating frame, but in a frame which has gravity, i.e. the surface of the Earth, and I have an emitter of light sending the light, say, upward, and it goes up a distance h, and I detect the frequency after it's gone up a distance h, I will detect a change in the frequency of that radiation because of the Doppler shift, using the equivalence principle relating the accelerating frame to this gravitational frame. And so that's an important result. That's telling me that light that's being emitted from deep inside a gravitational well, like on the surface of Earth, going up, is changing frequency. Now, it turns out this is a very small change, at least for Earth. Nevertheless, it was measured. So this Doppler shift for light in the gravitational field at the surface of the Earth was tested by Pound and Rebka in 1959 using gamma rays. And they had a source of gamma rays and a detector on both above and below a tower. So you could send the gamma rays, say, from the top of the tower down or from the bottom of the tower on up and detect them. Now, the tower they used had a height of 20 meters, and sending the gamma rays down means dropping the photons, if you like, to the ground where you have your receiver. And they can measure the frequency shift. And that calculated frequency shift and what they're trying to measure, delta f over f, for a 20-meter height, plugging in the speed of light squared in the denominator and the acceleration due to gravity of 9.8 meters per second squared, was just 2 times 10 to the minus 15. That's a very tiny fractional change in the frequency. It's very difficult to measure, but nevertheless it was verified, this calculation, by making use of some interesting quantum mechanical properties of detectors. There's an effect called the Mossbauer effect, where when the photon of that light, that gamma ray, is absorbed by an atom, well, the atom obviously has to recoil to conserve momentum. But that would give you a big uncertainty because of, if you like, the uncertainty principle. But if that energy that's absorbed is absorbed by all atoms making up that detector collectively, then it can still receive the same momentum, but the given absorption of that will have a less variation to the uncertainty principle. Anyway, long story short, they were able to see this very, very tiny fractional change and see that indeed light changes frequency going up or down a gravitational field. And so actually, that means that there's a Doppler shift, say, for us on the surface of the Earth for light being sent to satellites and vice versa. For example, in orbit about Earth are the satellites that comprise the GPS system that allows us to locate ourselves on the globe. But because that radio wave is being emitted from a satellite, hundreds of kilometers, if not thousands of kilometers above the Earth, by the time we receive it, we have a different frequency. And we have to account for that. If you do not, then over time, significant errors will accumulate, right? So to locate yourself, to within a precision of a few meters on the surface of the Earth, so your ride share can find you and pick you up, right, using your cell phone, you have to have the devices account for this general relativistic correction due to this Doppler shift. So very interesting. We're actually testing general relativity even just by calling up a ride share to our location. And finally, let me just say that another way to equivalently think of this Doppler shift is that as you send the photons that comprise your light up or down, they are either gaining or losing gravitational potential energy. So a completely equivalent way of thinking about it is the energy of a photon, which is either gaining gravitational potential energy or losing it as it goes up or down, respectively. All right. Finally, let's do some relation of Doppler shift to the concept of time dilation. If you remember in special relativity, reference frames that have a relative velocity between them, there is a time dilation for the observer in one frame to see the clocks in that other frame. It turns out now the same occurs for frames that are in different locations in a gravitational field. And we can understand this time dilation by realizing that frequency, right, so many cycles per second, is just the inverse of period, a period of time. So it's actually one and the same thing, just one's the inverse of the other. So for light traveling up a distance h from the surface of the Earth, as we were just discussing, remember the change in that frequency, relative change, delta f over f naught, was minus gh over c squared. And let's just rewrite that in terms of the period, because period, relationship between frequency and period is f is 1 over t, where t is the period. So just expanding out my f minus f, my delta f is f minus f naught. I can write as f over f naught minus 1. But then using that f is 1 over the period, I can write f over f naught as t naught over t. The period in the frame of the emitter over the period observed by the detector, minus 1. And that number we saw, the effect of that is minus gh over c squared, as I just said at the beginning of the equation. So t naught over t itself, the time in the emitter's frame over the time measured by the receiver is 1 minus gh c squared over c squared. But if I want to write it in terms of the time period measured by the detector's reference frame relative to the emitter's reference frame, let's invert that and solve for t. So just inverting the equation here, I want t in terms of t naught, so it'll be t equals t naught over now 1 minus gh over c squared. So just inverting that one. But I can simplify things a little bit. This t naught over 1 minus gh over c squared. This is like 1 over 1 minus x. And I can expand 1 over 1 minus x as approximately 1 plus x for small x. So the denominator here, if I treat gh over c squared as my x, I can write this 1 over 1 minus x as 1 plus x. So it's 1 plus gh over c squared times t naught, the time in the emitter's frame, when the field is weak, when gh over c squared is small. And that lets me then write, if I subtract t naught off from both sides, t minus t naught is just going to be gh over c squared times t naught. So this equation here. So I have the change in the period time from the emitter's frame to the receiver's frame. So what that means is the clocks at the bottom of a gravitational well appear to run slower, meaning larger t, delta t is positive, so it's t minus t naught, appear to run slower as viewed from the reference frame at the top of the well. Okay, so we measure a longer period, so as we measure the light coming from the lower part of the experiment, looking down on the Earth, say, the Earth's surface, we measure the period here above at the ceiling, higher up above the surface of the Earth. The period is longer. The delta t is positive than t naught when it was emitted. So it appears that I put this known watch down in the gravitational well near the surface of the Earth, and now it's slowed down by gh over c squared, where h is the height above the surface of the Earth. Or put another way, right? Here's my head. My feet are down on the surface of the Earth. It means my head ages more than my feet. My feet appear to be time dilated. They're running slowly. The clocks, if you like, attached to my feet are running more slowly than my head, which is above by a height of, well, not quite 2 meters, a little under 2 meters. That's an interesting effect, right? Didn't know my head is aging faster, but it's not very big. If I take a 70-year lifetime, this is just a half a microsecond difference if I ran the clock for 70 years at my feet versus where my head is. So it's not a big change. It's not a fountain of youth for my feet compared to my head. Okay, but we can start to talk about some astrophysical objects where maybe these effects are larger. To do so, let's first understand how we can get further away from the center of the massive object, where the gravitational field therefore will be changing. So we have a non-uniform gravitational field. So if that gravitational field varies substantially from one location to another, we can account for that by letting everywhere I place little g, acceleration due to gravity at the surface of the Earth in this case, by just big G, Newton's gravitation constant, times the mass of the object over the distance squared from the center of that object, r squared. I'm just going to do that substitution and recall that Newton's big constant g is 6.674 times 10 minus 11 newtons meter squared per kilogram squared. So that Newton's gravitational law, you'll get newtons out when multiplied by the product of the masses over the distance squared. Therefore, for light traveling a distance, say your distance r1 from the center of an object, and you want to go to a distance r2, which is significantly far enough away that you can't treat the acceleration due to gravity as a constant, we can rewrite that. And we can rewrite our Doppler effect, delta f over f naught, as being minus big G, the mass of the object, over c squared, times the quantity 1 over r1 minus 1 over r2, if you're going, say, from r1 to r2. If r1's smaller than r2, that means like you're closer to the center. And if it's the Earth, say you're on the surface of the Earth and you want to go to r2 where some satellite is a significant distance above the Earth, this would be the formula you use, replacing little g with the correct expression here. Likewise, we just showed that the Doppler effect can be related to time dilation, that clocks run slower, deeper into a gravitational well. So the time dilation formula changes. Delta t is big G m over c squared. Basically just remove the minus and make it a plus. Same expression, 1 over r1 minus 1 over r2 times t naught, the time naturally of the clock in its own frame. Now, if we're considering the effect between the surface of an astrophysical object of radius r1, surface of the Earth, surface of the Sun, surface of something else, to an observer very far away, suppose you're trying to observe the effects from our Sun, from the surface of our Sun to us on Earth. Well, R2 is effectively infinitely far away to a good approximation. So we could let R2 become infinity. 1 over infinity just becomes 0 in those equations, and they simplify. My Doppler formula is just delta f over f naught is minus gm over c squared over r1. And my time dilation formula, delta t, is gm over c squared r1 times t naught. So this is the case where I want to compare the time dilation effect or the Doppler effect from a distance r1 from an object to a distance infinitely far away. So it's, maybe it's another galaxy, for example. Okay, so let's give some examples of astrophysical time dilations, rather than the example of my head versus my foot. Before I do so, though, I do need to make one more correction, which is that if I talk about gravitational systems or astrophysical systems with very large gravitational fields, then my approximations made are not quite correct. And in fact, we have to go to general relativity to get the correct expression in the case of a strong gravitational field. And so without derivation, let me just say that the correction for the time dilation due to general relativity, so delta t, is 1 over the square root 1 minus 2 big G, the mass of the object, over c squared r1, the distance you are from the center of that object, minus 1, all quantity times t naught. So this is the correct general relativity expression for the time dilation effect. All right. It looks a bit different because of the radical than what I just showed you. But in fact, it does reduce to what I just showed you when the effect of gravity is small. So when you let this expression here, which is collected and call it x, when gm over c squared r1 is small, then you can expand this 1 over the square root term essentially as a binomial, right? So I can write that 1 plus x to the nth power is approximately equal to 1 plus nx when x is small. Okay? So if you do that, you'll find that this correct expression does boil down to my approximate expression before, shown here. So just an aside. But we're going to use the correct expression at least for, well, as you'll see, extreme examples. For our sun, it doesn't really matter, even though the sun is obviously much more massive than the Earth. The sun's mass, so abbreviate here m with a little sun symbol, circle with a dot in it. The mass is 2 times 10 to the 30 kilograms, so it's enormous. The radius of our sun is 700,000 kilometers as well. And despite that huge mass and this radius, the time dilation effect between the surface of the sun and, say, us on Earth, approximately infinitely far away, the change in time dilation is just 2 times 10 minus 6, the fractional change, delta t over t naught. So it's not a very big effect. It's 2 millionths of t naught, the difference. But let's talk about some other interesting objects. How about a neutron star? Well, for a neutron star, let's take a star that has the same mass as our sun, 2 times 10 to the 30 kilograms, but it's basically a star that's used up all its fusion energy. It's done all the fusion, is no longer energetically possible. It might make a supernova, and the rest of it basically collapses and compacts into effectively the universe's largest nucleus. And so it shrinks down to a radius of only 10 kilometers. It's 100,000 times smaller, approximately, than the radius of our sun, but has the same mass. So it's extremely dense, the density of a nucleus. Now we see that the time difference effect, the time dilation, is about 0.19 times t naught for a neutron star. And then we can say, well, what if it has even more mass when it compacts? What about a black hole? For a black hole, we can characterize a black hole essentially by the event horizon. This is the point of no return for a black hole. It's called the Schwarzschild radius. And it's given by 2 gm over c squared. And if we plug that into our correct expression here from relativity, we get that the time difference is infinite, in fact, because I'm going to have 1 over the square root of 1 minus 1, which is 1 over 0, which becomes infinite. Oh, strange. So in summary, what I'm saying is for something like our sun, the time dilation effect from the surface of our sun to a distance far away from it is only that the clocks run 2 microseconds per second slower on the surface of our sun than away from it. So putting a clock at the surface of the sun, if you could, you'll see that every second it's about 2 microseconds behind. Right, that's the 2 times 10 minus 6. For a neutron star, clocks run about 20% slower than far away from the surface of the neutron star. So a significant effect there. And for a black hole, essentially clocks have stopped. So if things are falling into a black hole, as you start to get very close, your clocks are running slower and slower, and by the time you reach this Schwarzschild radius, essentially it becomes infinite period. It stops. You don't see the object fall into the black hole. The time dilation effect stretches out, and for us observing far away from that black hole, it never gets across. And also the Doppler shift itself would become infinite, so the frequency of the light drops down essentially to 0. So it just becomes redshifted to the extreme limit. So it'll disappear from your vision as well. Of course, if you're the one falling in the black hole, time won't stop for you in your frame, but you also aren't going to escape, because it turns out at below the Schwarzschild radius, the escape velocity exceeds that of the speed of light, and you're essentially cut off from the rest of the known universe. So don't do that, okay? All right, that ends this lecture on the gravitational Doppler effect and time dilation.